In this lecture, we're going to continue to look at reactions of alkenes, moving away from the hydrogenation reaction to get into other broad classes of reactions. And so alkenes will mostly do addition reactions. And what I mean by that is if we take our alkene and we add it to some sort of molecule, let's call that molecule AB. A lot of times, what we'll see is that the carbon-carbon double bond will convert into a carbon-carbon single bond. And then the A and the B will break. One will add to one side of what was the alkene, and then the other will add to the other side of the alkene. Okay, so that's the general reaction. It's an addition reaction, where in many cases there are two things that add across the alkene. The double bond's gone. The single bond is still there, though, to make a carbon-carbon single bonded system with some new atoms. This is a very useful reaction for generating molecular complexity. So let's look at an example reaction. And a really good one to start with is the addition of HBr. Okay, so if we take an alkene, and let's pick ethene to start. So ethene is just ethane with an alkene. We're going to add to that HBr. Now, the outcome of this reaction is that we'll get a carbon-carbon single bond, and then on one side, we'll have the H from HBr. Maybe I'll highlight that just so we can keep track of it. And what that means is that the carbon still has its two hydrogen atoms. If I depict this as a tetrahedral geometry, then the opposite side, we have the bromine being added along with the two hydrogens that were there originally. Now, all of the hydrogens are connected to tetrahedral carbons as opposed to the planar carbons from the starting material. Okay. So this is the general reaction. Now, how do we understand this reaction? Well, what we should consider is actually a huge topic in organic chemistry, especially moving forward, and that is alternative depictions of the alkene. These are called resonance structures. Now, resonance structures are going to be a topic that we're going to hammer deeper and deeper and deeper into as we move through the course, okay? But just to start, what I'm going to say is that these are alternative drawings of a molecule. Okay, so what these do is they do a lot for us. They help to explain to us the types of reactions so that we can understand where electrophiles and nucleophiles may want to add on systems that don't have a dipole in nature. Okay, so in general, here's the approach. What we do is we take our alkene and we consider, instead of a carbon-carbon double bond, let's push the electron density. And I'm going to use a curly arrow to push the electron density to one side of the molecule, one side of the carbon-carbon double bond. That's going to give rise to a structure where now, if I consider the hydrogens, now we've got a carbon on the right with a lone pair. If we do formal charge calculations, we have a +1 charge at the left carbon and a -1 charge at the right carbon. And it's helpful to see to draw out the hydrogens so that you can see the formal charge calculation. We have a group 4 element -3 bonds -0 electrons equals +1 versus a group 4 element -3 bonds -2 unshared non-bonding electrons. That gives us a -1 charge. So what I've done is I've redrawn the molecule to show a different distribution of electrons. Okay, so let's capture that thought. So resonance structures, and I can't emphasize this enough, are just different drawings. They're just different drawings. That is to say, it's the same molecule. Now, what we're doing here is when we draw molecules, we're trying to capture something really complicated. Nuclei and electrons are scattered around this molecule in a pretty pretty interesting array that can be derived mathematically. And what we're doing when we draw something like this is we're trying to communicate the arrangement of all of those subatomic particles so that we can understand something. This took me about 4 seconds to draw. It's a lot easier than doing all those mathematical computations. Okay, this is just a model. There's going to be some error. An alternative way, what we could do to try to minimize some of that error, there's still error, is to consider alternative drawings to try to capture different thoughts. Now, one of these drawings is one in which carbon-carbon double bonds are not depicted as two bonds between carbon atoms, but rather a plus charge on one carbon and a negative charge on the opposite carbon. These are the same molecules, so I have to be careful about some formalisms. What I'm going to do is show a resonance arrow that is a double-headed but not equilibrium arrow. It's double-headed on the same line. That is my resonance arrow. And that's trying to communicate to you, the audience, that these are the same structures. And if they're the same structures, I need to be mindful of that. This isn't a different structure. I haven't made anything new. I'm just drawing something different. The true structure of ethene is some combination of these two structures I have written on the paper or on the screen. Okay. Again, I just want to emphasize we've come so far with drawing molecules with C's and H's and lines. We've come very far, a few dots here and there, with this kind of Lewis dot formalism. But there's going to be some shortcomings, though. And one way to address the shortcomings, one way to address the error is to draw multiple depictions of the same molecule. The same molecule. What I have shown here are two molecules that are identical in every property. They're not different, but they allow us to see the molecule in a different light. You can kind of think about it as turning like a jewel over or something. You see it in a different angle, you get different light reflecting, but it's still the same jewel. I don't know, some metaphor. With these charges, we can start to see how this thing will react with a molecule like HBr. That is, if I let this come into contact with HBr, which is a strong acid, we have dissociated, and by strong acid, I mean, if we introduce HBr, it's going to readily dissociate to form H plus and Br minus. Now, the negative charge is attracted to the H plus being a single subatomic particle, reacts first. That's going to give rise to this structure, which now has a positive charge left on one of the carbons. Now, this structure is different. It has engaged the H plus. That allows us to then think about how the Br minus might go ahead and add to the carbon atom. So the Br minus will then add. We always draw arrows from our negative to our positive, as that shows the movement of unshared electrons, non-bonding electrons to the carbon atom in this case. That's an electron acceptor. It will receive the electrons. It is electrophilic to form a new bond, and that will give rise to yet another new structure. So the first two drawings I've done in the top parts of this page that you can see are the same structure. It's just shown in a different light, a different distribution of electrons, but the nuclei themselves have not changed locations, okay? The bond between the two carbon atoms is not a single bond distance. It is a double bond distance, okay? So nuclei haven't changed positions. We're just redistributing the electrons. Now, what's important to note is I've drawn one possible resonance structure all along the top. I've drawn one possible alternative structure. But if we go back to our general consideration, or if we go back to our general alkene, let's actually take two routes. I'm going to draw this in the center of my page, and I'm going to draw a resonance structure going to the right and a resonance structure arrow going to the left. So I show that with these double-headed arrows that are not equilibrium arrows. We're not doing an equilibration process. Okay, we're not going back and forth. We're just redrawing, trying to increase our understanding of these molecules by drawing them in different ways. Okay. So what I could do is I could have the lone pair resulting in a negative charge on the left, or excuse me, the right, and then the positive charge on the left. But alternatively, I'm going to call this B and B. I could go to the left with my lone pair of electrons and put the positive charge on the right. Now, what that does, in effect, is provide another way of depicting our initial molecule. So while everybody in the class, if I gave them the formula, they would give me an alkene, something like this, with no separation of charges, we say. No charges present. If there's a negative and a positive next to each other, let's cancel them out. Let's make double bonds. But an alternative depiction would be one in which we have the charges separated, positive charge being on the right or the positive charge being on the left, countered by the corresponding negative charge. Now, what I want to point out about these two depictions is that with this R group, with this non-hydrogen atom, we now have an opportunity to form either a primary cation or a secondary cation. Well, it's not really a cation. It's a different way of depicting the exact same molecule that has an overall neutral charge. It's just we could put, instead of, it's not really a partial positive charge because that's derived as we would typically think of it, because that's derived from a difference in electronegativity, which we're not seeing in an appreciable degree here. Instead, what we would say maybe is that this is a better spot for an electron deficient center. It's kind of like our distorted epoxide that we saw previously, where when we protonated the epoxide, we weakened the bond, okay, at the site that was more substituted, because that could give rise to a more substituted positive charge. But the positive charge isn't real. Rather, there's sort of a buildup of positive charge-like character. We're making that carbon less electron rich, maybe more electron deficient. It's becoming electron deficient because it can handle not having as many electrons with hyperconjugation from the neighboring groups. Okay, all this said is if you compare both spots where the cation could be, you get to a better resonance structure. And so what happens if we move away from ethene, our original example, and into something that has substitution? What happens to the reaction of an alkene with HBr? Well, let's consider that. Let's just keep an R group. Now, if the R group reacts, I'm going to leave a space here. Well, I'm just going to draw a resonance structure in a second, but I'm going to leave a space here and let this react with HBr, which I'm going to start by just showing as H plus and Br minus. Now, what I want to do is consider a better resonance structure than the one on the left. So this one on the left is worse. The one on the right is better than the one on the left. And so I put my positive charge here. I put my negative charge here. Well, when we consider only the better resonance structure, it seems like the negative charge on the right carbon will attack the positive, meaning that we'll build up positive charge character. We'll actually form a carbocation intermediate at the more substituted position, which is more stable. So more stable cation, which is good because we have substitution. And then when the Br minus comes in, it has only one opportunity, and that's to attack the positive charge on the left-hand carbon. So when HBr adds, while it's possible to add to either side in terms of both carbons look the same from one depiction, it turns out that one carbon is more electron rich and ready to accept the hydrogen cation than the other one. And so we'll see Br only go to one side. This is actually a general rule, and it's called the Markovnikov Rule. And this is an important concept in this class. Markovnikov Rule. What the Markovnikov Rule says is that under acidic conditions, H plus goes to the less substituted side of an alkene. And then the nucleophile goes to the more substituted side. Okay, I'll let you catch up there. Okay, so what that means is that when we have our generic alkene reacting with HX, we're going to see the selective formation of a product where X goes to the more substituted and H goes to the less substituted. Now, while in terms of the arrows, in terms of the possibilities just from our non-resonance depiction of the original molecule, it seems possible that the lower structure could form, but it does not form under these conditions. What we say is that is the anti-Markovnikov product. It violates, Markovnikov is a person, so I should capitalize this. The anti-Markovnikov product violates the Markovnikov rule, and we say that it's not formed under these conditions. There are conditions that we'll look at in the next module where you can enforce the formation of the anti-Markovnikov product. Okay. So it turns out that the Markovnikov rule is fairly robust. Now, what sort of underlies the Markovnikov rule is number one, the acid reacts first to form the more substituted carbocation. The carbocation intermediate let me just write this before I say this point. I just want to remind us that the carbocation intermediate is an actual intermediate. It's not a resonance structure. So that first positive charge right next to a carbon with a negative charge, that was a different way of depicting the starting molecule. It's not an intermediate. Whereas the carbocation resulting from the intermediate, resulting after protonation of the alkene, is actually a full-blown intermediate. And so we wouldn't draw that with resonance arrows. Okay. So this reaction, the overall reaction that I've been showing you, is called the hydrohalogenation reaction. And it's not hyphenated, but I did just to emphasize that hydro means H plus, and then halogenation means X minus. So these names are not names of people. They are just names to kind of remind us what's happening in the actual reaction. One could argue a lot more useful than like a name reaction or something like that. I mean, what is Diels and Alder really telling us about the bonds that are being made and broken during the course of the transformation? So the overall reaction, hydrohalogenation. Let's look at another example of this before we move on to the next reaction. If we have this and we react this with HI, we could think about what are the products being formed. So in this case, what I would want to do is first draw a double-headed arrow to show a resonance structure that allows me to understand how these things are going to add. To do this resonance arrow, I'm going to plop the electrons either to the left side or the right side. If I push the electrons in the lone pair over to the right side, I make a formal negative charge on that right side, and a positive charge is on the more substituted carbon. So this is tertiary. Again, it's not a full-blown positive charge. This is just a different way of depicting the molecule that's better than us putting the negative charge on the left and the positive charge on the right. One thing I'll always emphasize is that that starting structure with the carbon-carbon double bond, that is the best depiction that we can do on paper, but it just doesn't give us any insight as to why H plus prefers to go on the right. So we consider the second best depiction, which is this charge-separated molecule, showing us that if H plus is present, and H plus comes from the fact that HI exists in a favorable equilibrium towards dissociation of the two atoms to give H plus and I minus. The H plus is going to be attacked by the lone pair of electrons from the pi bond. That's going to put a positive charge at the tertiary position. And we've made the most substituted carbocation and the most stable carbocation by considering by considering appropriately the resonance structure that gives rise to the positive charge being at the tertiary position. Then the iodine can come in and attack. That would give rise to this structure as the product. Now, an alternative mechanism that actually does the exact same thing for us, but it's just not as insightful, I'll say, is one in which we have this reacting with HI, and we have either the pi bond directly attacking HI and pushing electrons onto the iodine, or we consider the dissociated pair of ions. And in either case, the pi electrons are just reaching out and attacking the hydrogen. And that's going to give rise to the exact same intermediate. We just have to know that the pi electrons, when they engage that hydrogen atom, are going to put it on the right carbon that was double bonded as opposed to the left one. Okay, so this is sort of a little bit less clear. I prefer in the early stages for my students to consider resonance structures, alternative depictions, because that'll only help us down the road, and it seems to clarify things as to which carbon we are going to have get protonated. Now, if we just remember the Markovnikov rule, compare the two carbons, the left one being more substituted, we know that's where the iodine is going to go, and then the H plus goes on the right side. Okay, we get to the exact same intermediate, which can be attacked by iodine too. I guess I'll just redraw it. To show the formation of the product. So what we can do to kind of mix things up a little bit is to consider, what if we do this in water with an acid that doesn't have as good of the acid that's used in low concentrations or doesn't have a nucleophilic conjugate base. Okay. So this is called the hydration of alkenes. Okay, so what we're going to do in the hydration of alkenes is we're going to do virtually the same reaction where we add H plus, but instead of adding X minus as we did in the hydrohalogenation, we're going to replace that with H2O. Okay, H2O. So we can remove X minus by replacing HBr, HI, HCl. We're going to replace those with H2SO4, HNO3, and H3PO4. And these are, I'll just say this, these are acids with a non-nucleophilic conjugate base. That is, the conjugate base is the negatively charged thing that results when we lose H plus during an acid-base reaction. Okay, so we lose H plus, we get something that's negatively charged. That thing is the conjugate base. If you recall from Organic Chemistry 1, it's a little bit bewildering, I guess, but X minus is both a good leaving group, but it's also a good nucleophile. And we took that to our advantage when we looked at the hydrohalogenation reaction. So the halogen is a good nucleophile. If we just replace it with something that's not as good of a nucleophile, like the conjugate base of sulfuric acid, which is sulfate, nitric acid, which is nitrate, and then phosphoric acid, which is some sort of protonated phosphate, all of those are not good nucleophiles. And so we won't see those competing to add to the positive charge that we would build up during our Markovnikov hydration reaction. So what's the outcome of this reaction then? Whoops, looks like I have to make some new pages, sorry. Nope, now it's doing that awkward thing. Okay, so what's the outcome then if I come back to this and I say, let's add to our alkene H2O and some sort of H plus, and it turns out this can be a catalyst. So that means we could probably get away with HCl, HBr, or HI because we wouldn't have that much of the conjugate base floating around, the concentration of the water would probably beat it out. But just in case, we can pick H2SO4, H3PO4, or HNO3. Strong acids that don't have a conjugate, a nucleophilic conjugate base. Now what I want to do is I want to consider a resonance structure where we put the electron density onto the less substituted position and put the negative charge in the less substituted position from the carbon-carbon double bond. This is just an alternative depiction of the exact same molecule, but allows us to see why the H plus would be attracted to the terminal carbon or the less substituted carbon. That would give rise to, I'm going to go down a little bit. I'm going to need just a little bit more space. We have one additional step, but we're going to give rise to the more substituted positive charge, and that's going to engage one of the lone pairs from water. So the water's going to donate electron density. It's going to serve as a nucleophile attracted to that positive charge, the electron deficient center, and that positive charge is going to be an electron acceptor for the lone pair of electrons on the water molecule to give rise to this structure. Now we've seen this before where we have an oxygen with two hydrogens and a bond to carbon. Okay, we could either lose that oxygen, which would just be the reverse event to give rise to water off the molecule, or we could lose a hydrogen. The hydrogen is going to slip away by allowing its electrons to be absorbed by the positively charged oxygen atom to give rise to our final product. And we continue to draw that hydrogen explicitly. Now have an unshared non-bonding pair of electrons, another lone pair, you could say, and we release H plus to show that H plus is both the starting material and the product of a reaction, definition of which is a catalyst. So the H plus is a catalyst for this type of reaction because the H2O releases a hydrogen after it adds. Now the net addition of OH and H across what was our alkene center is kind of like we're taking the alkene and adding H2O across it, or water. And so we call this the hydration reaction. So it's a hydration reaction because we do a net, I call it net. It's not like we added water. Water would not add at an appreciably practical rate unless we had that H plus to catalyze and speed up that transformation. So it's the net because we do a net addition of H2O, and I like to write it HOH, which, I mean, of course that's water, but we didn't just take water and just snap it right on. We required some H plus to actually promote and catalyze the reaction. Okay, so that'll do it for our first round of addition reactions to alkenes. You'll notice that the hydration reaction also followed the Markovnikov rule. I should just write that down explicitly. Sorry, I'll get the notes back in front of us. So this follows the Markovnikov rule. So here we've just replaced the nucleophile. Instead of being a halogen, it's the oxygen from water. Okay, so that will do it for the reaction, or for the lecture. Goodness. And notes over that reaction. We'll move on to different reactions in the next lecture. Okay, everybody have a great day.